Hello, I'm Drew. I'm a third-year Gator engineer, and today I'm going to be teaching you guys how to derive the kinematic equations. So these are the four kinematic equations you have that you'll probably use in your physics class, and they're going to tell us how to find the position of some object with respect to time if we know its velocity and its acceleration. So, we've got a car, and we describe its position as x. So x of t equals position. And that makes sense. It's a function of time because it's changing with time. V of t is equal to our change in x for a change in time. We have this triangle here, the dt. But if we think about it, so we have xi as our initial position. So delta x, or triangle x, is x final minus x initial. And delta t is t final minus t initial. And if we think about it, t initial, we start our problem at time equals 0. So we don't need to have that t initial. We don't need to denote t final because any t is our t final. So just, for reference. And then similarly, our A is delta V delta T equals V final minus V initial over T. So the same way that, velocity is the change in position with respect to time, acceleration is the change in velocity with respect to time. So we'll start with a super simple example, and we'll get some intuition from that, and then we'll do a little harder of an example. So first, the simplest problem we can really think of is, let's say our car is moving to the right at a constant velocity, and we say that constant velocity is v initial. Did that cut off? That did cut off. So you can't see that constant velocity, but it's v initial. And its position at whatever time t is x final. So at time t, it's over here. Our car is here. So something that's really helpful for really any kinematic problem is drawing first a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. So for our problem where we said that our car is moving at v initial, that means its velocity is constant. Its velocity isn't changing. So a, which is change in velocity for a change in time, is 0 because our velocity isn't changing. So we've got, velocity is here. It's 0. Which means our velocity starts at v initial, and it stays at v initial the whole problem. Which means we have a constant rate of change in position with respect to time, which means that, y equals mx plus b, the slope of our x graph is going to be a constant, and that slope is going to be v initial. So, rise over run, we have delta x. That's an ugly x. And delta t. So the slope of that graph at any given time is v initial. And that slope is always constant because v initial isn't changing. So using our just definition of position, or definition of velocity, we can logically figure out where our car is at any time. So definition of velocity, v of t, is change in x over time. And since v of t is constant, it's not changing. The function v of t is just vi. It's v initial. And it's constant, which means we can multiply over our delta t, or just t. We have delta x equals v initial times t. And delta x, as we defined over here, is x final minus x initial equals v initial t. So x final equals v initial times t plus x initial. And we can see just looking at this, I wrote kind of small, but x final equals v initial t plus x initial. That's our equation right here when a is 0. So x final equals x initial plus v initial t. In the same way we defined v of t for change in x for change in time, we can also define, a of t equals change in velocity for change in time, which equals v final minus v initial over time. So if our car was accelerating at a constant rate, that means a of t would just be a. Then we could multiply over the t, and we have a t equals v final minus v initial. And then v final, switch things over to the other side. V final equals a t plus v initial. And if we look at this equation, so we've got this, we've got this. And if we look at this equation, that's our equation right there. Our final velocity is equal to our initial velocity plus our acceleration times time. So thinking about this logically, we said v of t is our change in x for change in time. A is our change in velocity for change in time. So velocity is, the slope of this graph, and a is the slope of this graph. Looking at it here, same way. And even the equations for constant velocity, or position for constant velocity, is the same equation as velocity for constant acceleration. It's acceleration is to velocity what velocity is to position, if that makes sense. But it'll make sense once I do more graphs. So that was just some quick intuition and explanation of what our equations really mean and how to use them. Now, let's have a slightly harder problem. What if our velocity wasn't constant? What if instead of an initial velocity that's constant the whole problem, we have, I'm just going to draw a new set of graphs. What if instead our car starts at velocity v initial, and just for the sake of drawing, we're going to say v initial is 0, but it doesn't have to be, and it has a constant acceleration a. So we have acceleration a. Velocity starts at v initial. For just this drawing, it's 0, but it can be anything. That means that our velocity steadily increases. So the same way for constant velocity, our position steadily increases. For constant acceleration, our velocity steadily increases. And what happens to our position? It's not going to be just a linear, simple line. It's going to have a small slope at the beginning. And as velocity increases, and velocity is its slope, it's going to start moving faster and faster and faster and faster with respect to time. So its slope here, isn't very much. Its slope here is bigger because velocity is bigger. So how do we find our position with respect to time if velocity isn't constant? Well, since we said, and this is an assumption that we make and that we need to realize is an assumption that we make, we assumed acceleration is constant. Otherwise, the math would be harder. If acceleration is constant, that means we have a linear graph here, and we assume this is linear, which means we have, for any v final, v final, whatever, wherever you want to put it, and v initial, there's a middle value that is our average of those two values, v average. And rather than saying we move slow over here and fast at the end, we can just use our average velocity in that equation over the equation that we derived here, this, and that works. Another thing that you can think of if you're more geometry, calculus savvy is you can say the area enclosed by this graph is going to be our displacement. And that's because our velocity is meters per second. It's change in x over change in time, and our time is seconds. So meters per second times seconds is going to come out to be meters. So your area is in meters per second times seconds. But for the average velocity case, which is I feel like a little easier to picture, we just say average velocity is equal to our initial velocity plus our final velocity over 2. And that's, for any linear thing, that's our average value. And if we use that average velocity in our equation, and that's basically, I'm not going to do that. If we use that average velocity in the equation we derived from this, v of t equals, x final minus x initial over time, and then algebrate it out, we got x final equals x initial plus v initial times time. Instead of using our assumed constant v initial, we use our linearized value of velocity, and we plug that in here. So we use our average velocity to get our time, our position. And so v average equals v initial plus v final over 2. Plug that in here, and we have x final equals x initial plus v initial plus v final over 2 times t. And we can define v final using this equation right here. Remember how we logically derived that equation? We had v final equals v initial plus a t. And we plug that in here, and we have x final equals x initial plus v initial plus v initial plus a t over 2. Oh, yeah, and then this times t. You're right, I didn't. Sorry about that. And then it equals x final equals, 2v initial over 2, so it's just v initial, and then times that t out here, plus 1/2 a t squared. Look at that. So we derived this first kinematic equation using our assumption of average velocity. And that assumption of average velocity, or that use of average velocity, assumes that acceleration is constant. And that's an assumption that we make. And for any problem that you solve, you have to recognize that if acceleration changes, like your car drives at 5 miles an hour and then stops, when acceleration changes, or when it accelerates and then you hit the brake, whenever acceleration changes, you have to write a new kinematic equation. But other than that, and that's totally doable, we can use this equation, and it will tell us our position with respect to time for a constant acceleration and an initial velocity. All right, so cut through erasing the whole board, and now I'm going to show you how to get these last two equations using our first equation. So from what we derived, we have that equation right there. And what is the value of these two equations? The nice thing about this equation is you have your final velocity and your initial velocity and your displacement without a time. You don't need to know how long your problem's been going on. You just need to know your final velocity, and you can figure out what your position is. In this other equation right here, you don't need acceleration. You just need your initial velocity and your final velocity, and you can have your position with respect to time. So how do we get rid of, first we'll start with getting rid of acceleration. How do we get rid of acceleration? Well, we have v final equals v initial plus at. And we can just solve it for acceleration and plug that into our kinematic equation. So v final minus v initial equals AT. And that means A equals V final minus V initial over T. Whoa. So use that and plug that into our kinematic equation, and we have X final equals X initial plus V initial times time plus 1/2 V final minus V initial over time, not times T squared. And so we've got the squared here, we've got over time, can cancel out one of the T's, algebra. And we math it out and we get X final equals X initial plus V initial T plus 1/2 V final T minus 1/2 V initial T. And so we've got a whole V initial T minus a half V initial T, and that gives us a half V initial T. X final equals X initial plus 1/2 V final T plus 1/2 V initial T. And we just rewrite that in the form of this. It's the same equation. We just, X final minus, subtract over the X initial, and X final minus X initial is delta X equals 1/2 V final plus V initial T. And look at that. We have the same equation right here, and we derived it by just solving for acceleration and plugging that in. Okay, so we're almost done. Now all we need to do is figure out how to get this equation without, by getting rid of all of our time, all of our T's. So what we're going to do is we're going to take this equation, which tells us, V final and V initial in terms of A and T, and we're going to solve it for T. So we have V final equals V initial plus A T. Solve it for T, subtract V initial and divide everything by A, and we have V final minus V initial over A equals T. Woo. So using that algebra'd out value of what T is, we plug it in to either this equation or this equation. Either this equation or this equation, and we can do whichever we want, but this one's a lot more math. It has, a T squared value. Don't want to do that. So we just plug it into this equation, but either works. And we have delta X equals 1/2 V initial plus V final times this V final minus V initial over A. And we're going to math this out, and we're going to get this equation, that equation. Delta X equals 1/2. So 1 over 2A, I guess, times V initial plus V final minus V initial. That's, the thing that you do when you multiply two things in parentheses. V initial, V final, minus V initial squared, plus V final squared, minus V initial, V final. That's all there, times 1 over 2A equals delta X. So that's when you multiply all of this out, we have minus V initial, V final, and positive V initial, V final, so they cancel out, blop, blop, and you have delta X equals 1 over 2A V final squared minus V initial squared. And then, in order to make it look cleaner and like this, we multiply everything by 2a, and I'm just going to take our equation over here. Multiply the 2a over, so we have 2a delta x equals v final squared minus v initial squared. And then all we have to do is multiply over the v initial squared, and we have, and switch the sides. So we have v final squared equals this plus v initial equals 2a delta x plus v initial squared. And we wrote delta x as x final minus x initial. We can totally do that if we want, just to make it look exactly the same. V final squared equals v initial squared plus 2a x final minus x initial. Woo. And we have our last kinematic equation. So that's it. That's our kinematic equations. And if you want to, if you plug in any of your values of a, v initial, v final, you can get your position with respect to time in a number of different ways.